So this presentation mostly comes from Greg Luke, our SYCL spec editor, who's been working on this feature for quite some time and builds on a lot of his work with kernel bundles and other things from SYCL 2020. So in this talk, we're going to be talking about the design and features of an online compiler for SYCL kernels. So let's start with, what is online compilation and why do we need it? So there are many applications that want to customize what they're doing based on the data, the features of the devices they happen to be running on, or who knows what other reasons. And there are already some things in SYCL that let you do this to some extent, and that includes features like specialization constants. However, that feature in particular has various limitations. Like, for example, specialization constants, while they have constant in the name, aren't actually constant from the point of view of C++, which means they can't be used in things like const expressions or as template parameters. Another way to try to solve this problem is you just enumerate all the possible options. So you can kind of predefine all possible variants of a kernel, all the different instantiations you may need. But depending on your application or what you're doing, there could be just too many variations, and that could lead to just an unmanageable code explosion. So what we'd like to be able to do is to dynamically generate source code for the kernels that we want to compile, and then compile it when the application's running. And this isn't a new concept. OpenCL has this. CL create program from source. That's been there for a long time, and other programming models have this as well. CUDA has NVRTC, HIP has HIP-RTC. All kinds of machine learning things are constantly spitting out C code or CUDA source or OpenCL source. So we've had a lot of people for years asking for this feature inside SYCL itself. So let's go through an example of what we're proposing here. So this slide basically demonstrates the idea, and it builds on the notion of kernel bundles that were added to SYCL 2020. So what this extension lets you do is you can now create a kernel bundle from source code that is passed as a string, which can define one or more kernels. And so, for example, we have some string source here, and then we have this new function, create kernel bundle from source, that takes the context that we want to bind this to, a specifier of the source language of our kernel, which I'll say more about that later, and then just the source code itself. Then once we've created our source code, our source code bundle, we need to build it. So we have a build function that will then compile and link the source code into a native device binary. So we can do that with our build method to get our executable bundle. And then once you have your executable bundle, you can query that to get a specific kernel, to get a SYCL kernel object out of it. So in this case, we want to get a kernel named myIOTA, and we'll get that out and have a SYCL kernel object. And once we have a SYCL kernel object, SYCL already has everything we need to go from there. We can just call the special overload of parallel 4 that takes the kernel object. And then for our arguments, we have to set those manually. So in this case, we know our kernel has 2 arguments. So we're going to set argument 0 and pass in some data, in this case, 3.14. And we're going to set argument 2 as some pointer. Now, there are a couple problems here with this approach, depending on kind of how you're using SYCL. And the first problem comes from the fact that if you attended the tutorial or saw many other talks, SYCL loves to use C++ lambdas. And there's a major problem with lambdas in C++ in that there's no ABI. So C++ doesn't specify how any variables that get captured in a lambda are ordered, stored, or accessed. It's a complete implementation detail, which can be very difficult when you're trying to do something like this, because, yeah, how do you know what argument is where? There's other problems in the SYCL spec regarding this as well. because because you could basically capture this thing effectively as a functor. And so you have a bunch of arguments inside that functor. From the SYCL point of view, do you treat that as a kernel with two arguments, or a kernel that takes a struct that has two arguments? It's ambiguous. So in order to solve this, we figured, well, maybe what we need is just yet another way to declare a kernel in SYCL. So that leads us to this new proposal as another way for kernel syntax, free functions. And what this is you can just define a kernel as a plain function, and then each function parameter is a kernel argument. Now the function needs to be decorated somehow to identify it as a kernel. In this case, we leveraged the DPC++ properties extension to achieve this. And here the property just says that this is going to be a one-dimensional ND range kernel. So again, like this isn't even too familiar, like if you're coming from CUDA or HIP, here's our version of __ global in some sense. So with this, we also need a new way for the kernel to get each work item's iteration ID, because we're no longer passing in an item or an ID. And we do this with a new free function as well. And we have an extension for that too. So in this case, we have this work item get ND item free function that we can use to get our item and then get our ID from that. And once you have this, we have several other functions to do all the kinds of things you would expect from this. Aside from these things, the rest of the kernel looks identical to any other SYCL kernel. And just one note on this, if you use this new free function way of defining a kernel, it's only supported for ND range and single task kernels, not for the simple parallel 4 flavor. And there is a reason for that. And it's kind of, it gets into the nitty gritty to some extent. So the thing about the ND range model is that when you're executing on a particular device, there are often limits to what the ND range can be. Devices often have limits to how many items can be in a work group and how many work groups you can have. And that can cause issues with simple parallel 4, because simple parallel 4 just says parallel 4, and here's a bunch of uint 64Ts that are going to express the range. And it's very easy to put a number there that's technically bigger than the limits of what your device may support. And so one option is you could just say, well, them's the limits and that's what you get. But users aren't always happy with this. They think if I can express it in C++, it ought to just work. So you can support this. You could support simple parallel 4 doing this in various ways. You basically just have to figure out how to map multiple iterations to one iteration of the ND range. But when you do that, it makes these free functions very difficult because you don't necessarily know what to return, which is why simple parallel 4 isn't allowed using the syntax. So if we put it all together now and take these new functions with this new free function kernel syntax, we can get a view of what the entire solution looks like. So in this case, it's the same sample as before, except we just expanded our little string source here to show a free function kernel encoded in this string. It's the same one from the previous slide. And then we proceed as we did before. We create a kernel bundle from that source, build it, get our kernel out of it, and then launch it. And now it's very clear what kernel argument 0 is and what kernel argument 1 is, because it's just the first argument of the function and the second argument of the function. And well, it's very nice that we can show this on a slide. The reality is most usage of this won't actually just encode it as a hard string like that. There'll probably be some mechanism that dynamically generate this in some fashion, either directly into memory or potentially it could spit out a file that then gets loaded into memory and passed in. But that's kind of just a usage detail. You can get the idea from here. So next we'll take just a brief digression on these free function kernels again. So while we introduced them in the context of online compilation, there's really no need to limit it just to that. You could just use this in a regular main SYCL program, just not as a string, just embedded in your single source C++. And so here our function iota is just another function in the SYCL program decorated with a property that says it can also be a kernel. And if you do that, when you compile this file, it will get compiled to device code when the application is built, just like any other kernel that may be in the program, be it a functor or lambda or whatever. And to launch this kernel, we again extend the kernel bundle framework. And this part is very similar to the online compiled case, except for the way we get the kernel object. Rather than calling the build function, we have a new overload of get kernel that takes the kernel's function pointer as a non-type template parameter. And once we have the kernel object, the rest of the code proceeds as normal. Yeah. So in this case, we just literally use the function pointer from the function and just pass that into a bunch of functions. And okay. So why would we want to do this? Well, it just gives us a nice consistent syntax between either regular offline compiled SYCL kernels and online compiled. There's just really no advantage in prohibiting the syntax in normal SYCL code. And we've even had users that would like this for other reasons, because even though we sing the praises of SYCL supporting single source C++, not everyone actually wants to use it that way. Another advantage as well speaks to the migration case. Again, if you're coming from OpenCL even, or CUDA, this just may look more familiar because it's closer to OpenCLC or how CUDA defines kernels. So it gives you an easier migration path. So now we'll go back to the online compiler part. So at the beginning, I mentioned the source language part of this create kernel bundle from source. And now we're back to that. So in the first example, we said our source language was SYCL, but there's no reason it has to only be SYCL. There's no reason we can't support other source languages as well. So for example, in this case, our source kernel is actually going to be a CUDA kernel. And it's defined using CUDA source code. And we just, when we create our kernel bundle, we say this time you're compiling from CUDA. And then everything else is the same. But now we're adding a CUDA kernel to our SYCL code and we're launching it with SYCL. And there's many reasons you may want to do this. It could be useful when migrating code or when you're migrating a CUDA code that's using NVRTC itself. Of course, it's a little trickier because if you have CUDA code in this, that CUDA code in the string may not be automatically migrated to SYCL, and yeah, there's further work to do. So, what's the status of this in our implementation? So we've implemented a lot of this today. So as a source language, SYCL will be supported on all backends. CUDA will only be supported on the CUDA backend because that's the way NVIDIA likes it. OpenCLC, of course, can be supported on an OpenCL backend or a level 0 backend because basically that just gets compiled to SPIR-V. So anyone that can take SPIR-V can use that. Which brings me to my next point. There's no reason that SPIR-V couldn't be a language. Because we've run into many cases where people may have some DSL that they're using to generate their own kernels directly as SPIR-V blobs. And then one of the problems we had with the kernel bundle interface was, if I have some SPIR-V, how do I get a SYCL kernel out of that? And so we finally closed that gap with these new APIs. So we just say that SPIR-V can be a kernel source language and everything else works exactly the same. So this is nice for a lot of reasons. It just basically gives ninjas a way to kind of hand code their kernels in SPIR-V. It makes it easier for, you know, DSL generators or other higher level languages. And it's just, the kernel bundles are finally complete, I'd say. So what's the status of things? As far as source languages go, OpenCL as a source language works today. SPIR-V works today. The SYCL support is currently under development, and the CUDA support will come after that. So we encourage you to give this a try. Let us know what you think. Let us know if it's useful. Let us know if you think it needs other features. And yes, the compilation time is probably going to be terrible. Thank you.
So the other models that support this allow you to pass in defines, so you could effectively do a little bit of pre-processing to get some constants into the kernel. Is that something you plan on adding?
Possibly. I'm not sure of the details, so I don't have a good answer for you. Okay. But it's effectively just using a Clang compilation flow at that point. So whatever Clang does, it's likely to support as well. And it like automatically includes various include files and whatnot, and you can specify extra includes to be included in the compilation unit and all that type of stuff.
Hopefully a simple question. So for the online compiling of, can you declare multiple functions that are kernels?
Yes.
Okay.
And then when you want to get the SYCL kernel object, you just identify the specific one in that kernel bundle.
So I agree that there's a use case to have something in SYCL that's more powerful than we currently have a specialization constants for JIT time optimizations. So my question is maybe a bit more provocative. How is this not putting a lot of engineering effort into reinventing what basically is already OpenCL? Like if you want to have a separate source model, wouldn't it be a better investment of time to just, you know, make sure that OpenCL works better, is more portable and so on, instead of, in the worst case, undermining efforts to revive OpenCL, such as Rustical, for example?
You could say the same thing about SYCL in general.
Oh, no, I disagree. SYCL is a single source model which fits a very different niche. And I think you could also solve some of these issues that specialization constants are too limited within the single source frame of SYCL.
I don't disagree. Yeah, this is one of those weird things where initially we were very hesitant to do it because we knew it would have certain drawbacks and be kind of a big engineering effort. But for some reason, there were many people that wanted it. And then there was also a class of applications that unfortunately heavily used this type of capability, AI. So when trying to integrate a SYCL toolchain into a lot of AI workloads, we find this functionality is a requirement. Yeah, and the single source thing, like I'd say it's great that SYCL supports it, but we shouldn't necessarily require it if a user doesn't want it.
I think we may have disagreement about what SYCL is.
So taking it a step further, compiling from binary after you've done it once, like OpenCL has, so you can save your compiled runtime compiled code, and then you talked about
okay.
performance. Is there
Yeah.
any thoughts of that?
Many implementations have caches, either in memory or on disk or both. And I think the binary case actually is was already handled by the kernel bundles, like potentially there's nothing stopping you from loading a binary from disk and just shoving it in a kernel bundle.
Yeah, to go back with Axel, yeah, I'm surprised too, but a lot of people at Argonne also ask for this exact same feature. And I always tell the same thing as you, and others, well, they say, no, I've used SYCL, I want to use SYCL. I mean, what is the point? If not, I go back to full OpenCL and I will not mix and match, right? And or we'll go back to CUDA. And so I think it's useful to have it for better or worse. I would have really preferred that we don't need this kind of feature, but look like it is a request for the user.
Yeah.
What am I to decide? Yeah.
I agree. I was initially very hesitant for years, but our users want it, and who am I to disagree?
I just want to add something to what James said. So, great presentation, but the documentation, the extension specification are really deep. So, if you are interested, I would visit, because, for instance, for passing defines, there are properties for that. I think you can use build properties to passing defines. That's already in the spec, so that's a way to do that. And I also agree that, I mean, I have been looking into port DNN for my poster there, and the spec constants are really not enough. And I think this is a really cool extension, and they could be really helpful in workflows like port DNN, where you need a lot of kernels that maybe you have to even generate at runtime. So this is really needed, and yeah, this will be used by users. So that's what we care about, I think.